Good morning. We have another midterm coming up. Let's do some review problems. We had done this on midterm 1, and I think it worked out pretty well. Let's go ahead and take a look at some review problems. Now, what these consist of, these are problems taken from a midterm from several years back. And we've got a couple of these. So here is one of those midterms with 4 problems. We'll look at that during the first hour today, and then we'll come back after the break and look at another set from another midterm. And we can expect that our midterm will be very similar in terms of format. So I'm guessing that we'll have 4 questions, and that the questions will have parts A, B, C, D to them, something similar to this. So let's go ahead and take a look at these problems. So here we go. Now, what we've got coming up on the midterm here is, you guys have taken a midterm now, so you have some familiarity with how this works. But we're looking at, we've got chapters 27, 28 that we're looking at magnetic forces and magnetic fields. And then we got 29, which is looking at generating electricity. And then chapter 30, that's looking at a new device called an inductor. It's defining what inductance is. And so now at this point we have resistance and capacitance and inductance that can show up in a circuit. And we're looking at both DC power supplies, we're continuing to look at those, and we've added in AC power supplies. So yeah, let's take a look and see what we've got here. So it looks like on this problem, just very, very generally, we've got a problem looking at magnetic forces. We're looking at a problem here where we're looking at magnetic fields and relating the magnetic fields to electric fields, which will allow us to generate an EMF or a voltage. And this is an example of like an electric generator. How do we build generators that can generate a voltage or generate an EMF? Because hey, when we plug into an outlet, we're expecting that we have access to electric energy through that outlet. And then we're coming back and looking at a circuit. This looks like it's an AC driven circuit, so we have an AC power supply. And then finally in chapter 31, we are looking at the propagation of electric and magnetic fields. So electric and magnetic fields propagate, and that's actually what light consists of. So it turns out that the full spectrum of light, not just the visible part, but infrared, ultraviolet, X-rays, gamma, and in this case microwave and radio, it's all done with electric and magnetic fields. It's all done with particles called photons that we'll be discussing not too far in the future now. So we're headed in that direction, looking at the properties of light. So anyway, that's kind of the overview here. Let's go ahead and get started with that first. So it's a lot of stuff, so I should say that again too. As I keep saying in class, we're just going through a lot of stuff in this course, right? A lot of topics that we're hitting. So thank you for all your work with this in getting through all of these topics. I hope they're interesting, and I hope that they're going to be useful as a foundation for other work that you do in your other classes. So we're looking at a magnetic field region. Now, to be specific here, what we've got is, I've kind of grayed this out. That's the magnetic field region right there. So we've generated a magnetic field region. And then what we're going to do is we're going to take a set of wires. Now the wires have current going through them. And so there is a current going through this wire. So what I really should do is I should have some wires going off to a battery or something. I should have a battery that's driving this current. So this is not an example of generating a current, somehow using that magnetic field and magnetic forces. Instead, this current is coming from somewhere else. I got a battery out here operating this current, and then I'm going to take this current, place it in the magnetic field region. And what we've learned in chapter 27 is that if I have charges moving in a magnetic field region, they're going to have forces acting on them. And so the key formula for this would be the force that these charges going through here experience is given by the current. I can work directly in terms of current. I don't have to go back and think of the charges on the electrons and how many electrons. That's taken care of for us once we've identified how much current we have. And so in this problem, it says that there's actually 12 wires. So this wire has been wrapped around so that there's 12 loops closely spaced together. So I've got 12 wires running through here. Now the length for this formula, we're only going to get a magnetic force where there's a magnetic field. And so I don't want to use the 18 centimeters. I want to use the 13 centimeters. This is the region where the force is being is going to show up. So I'm going to end up with a force along 13 centimeters of distance. That's going to go in for my length. And notice that I've put that in standard units. So again, we are hitting a lot of topics, and we're introducing a lot of new physical quantities. And I'm going to say, stick with standard units. So stick with standard units, get everything converted into standard units in your problems, and then stick with that. And so that is now 0.13 meters. The magnetic field, we are told, is 1.35 Tesla. And the mass of this entire object, now this is placed vertically. So just to make sure that we're clear on the orientation, it talks about that. So I've got a magnetic field that's running horizontally, and then I'm going to take this and place it vertically. This is hanging down. So there's going to be a magnetic force that lifts up this portion of the wire as long as the current continues to run. And so I've got wires out here to a battery, and I've closed the switch. So current is going through here, one way or the other. I guess we have to determine which way that would be. But as long as we have current going through there, and there's a magnetic field region, we're going to get a force. And so the force here is going to be given by N times I times L times B. What did they want us to solve for? Oh, show the direction. So at first, we're just doing the diagram stuff, right? So what we need is this. I've got a gravitational force. Gravitational force is downwards. So that gravitational force is directed downwards. And so I need an upwards, vertically upwards magnetic force to balance this out. We're going to make this thing hover, I guess, is what we're calling it. So it's going to hover because of the presence of the magnetic force. Now, so the magnetic force needs to be up. We're told the magnetic field is into the page. That's what those X's are showing. And so I have to bring in a right-hand rule. So I'm going to bring in the right-hand rule. Now, if I think the way I defined it is if the current's going in the direction of my thumb and the magnetic field is going in the direction of my fingers, the force is coming out of my palm. So the force is directed away from my palm. So let's see if we can arrange this. So I am going to have my palm facing upwards because that's the direction of the magnetic force. So my palm is facing upwards. Now it does turn out that my fingers in that case are going into the board. I could move these around, but I need them to go into the board because that's the direction of the magnetic field. So in order to generate a force upwards, using a magnetic field oriented that way, the current needs to be to the right. So the current needs to go this way. That means I need to set up my battery oriented in a way where the current through that upper region passing through the magnetic field is moving from left to right. So, so that is the diagram, and this is the cross product formula. In part B, they are saying label the diagram with the forces at, okay. So here is that set of wires, and the force of the magnetic force needs to be up, the gravitational force is downwards. I need the force, due to the magnetic field, to match the gravitational force. Now how have we done that? And I set up the formula. So here's the magnetic force, here is the gravitational force. I'm solving for I. Now what I ended up with on this side was mg. So I did get a chance, this is 2.4 kilograms, right? Okay, so that's a fairly heavy set of wires. I would not have expected it to be that heavy, but it is. And so it's 2.4 kilograms, and multiplying that by g gives us a downwards force, gravitational, of 23.5 newtons. That means that the magnetic force needs to match that. We need to turn up the current such that the magnetic force is 23.5 newtons, and that formula is going to do that for us. It's going to tell us how much current we need. So we're going to need 11 amps. So 11 amps, that's a pretty good current. You know, that's like a vacuum cleaner or a toaster or something like that. Something that's using a hair dryer, that's using quite a bit of electric current. But that's the current that will maintain enough magnetic field to make this set of wiring hover. This 2.4 kilogram wire, which is quite a bit. Okay. It's a good sized magnetic field we've got, 1.35 Tesla. I think we've mentioned that too, that the Teslas are pretty good sized units. So even 1 Tesla is a lot of magnetic field. Okay, that sounds good. Let's move on to the next problem. So in problem 2, this one is generating, this is using I'm going to say electric field. Let's talk about this a bit. So this is using electric fields to generate a current, and I'm not sure which way the current. Let's see. A circular loop. I should read the problem. A circular loop of wire. Is it just one loop? That would help, because I always forget to put in the number of loops. Increases. It's in a region of a magnetic field. And the magnetic field we can measure as going from minus 800 millitesla to plus 800 millitesla. Now, it's a little ambiguous about how to interpret the diagram. I'm going to interpret the diagram as initially the magnetic field is into the page, the way it's drawn. So I'm going to say that's what the magnetic field initially looks like. But notice that during the interval, the time interval of 2.5 seconds, the magnetic field reverses direction. Now, it doesn't really, what's important for us here is not so much that it reverses direction, but rather, what we want to be able to think of conceptually is, what does the magnetic field look like as a function of time? And if it's going from oriented into the page to oriented out of the page, and it's happening linearly, what we can do is we can draw that graph. We can draw B as a function of time and say that the magnetic field, we're going to say the magnetic field is increasing, or the function showing the magnetic field has a positive slope. Now the reason we're interested in the slope is because Faraday's law says that if we can keep track of how the magnetic flux is varying, that will tell us how much electric field is being generated, and as a result, how much EMF we'll have. So, so I'm going to start off by saying this. I'm going to take dB dt, because Faraday's law tells us that if we keep track of the flux, not the flux itself, but the time derivative of the flux. So I'm going to write the flux as B times A. It's a uniform magnetic field. There's a certain area contained within that loop that we've drawn. I can take the time derivative of that. Now the area is not changing, but the magnetic field is. And so I can bring out the factor of A. I'm going to keep the minus sign here. There's the factor of A. And then what I end up with then, in terms of taking a derivative, is dB dt. Now dB dt I can think of as just delta B over delta T, and that's because the magnetic field is varying in a linear fashion. So it's a steady rate of change occurring in the magnetic field. And for those examples, we don't have to use any rules from calculus. We can just say that the rate at which the magnetic field is varying is, there's a net change in the magnetic field of 1600 millitesla, and that happens during an interval of 2.5, and it's at a fixed rate. And so dB dt becomes 0.640 Tesla per second. And so now what I want to do is calculate the area, get the area calculated. Now, I'm going to drop the minus sign for right now and say that the magnitude of the EMF that we're generating is equal to the area times dB dt. Putting those numbers in, this is standard units. This got converted into meters squared. This is in Tesla. This is going to come out in volts. And so I did a quick switch and put it back into millivolts because it was a small number. So this is working out to be 29.0 millivolts. So it's not a huge voltage that we're generating here. Now conceptually, just to be clear, what is it that's changing? What is it that's actually driving the current in this? Oh, let's move on a little bit more, and then we'll come back and talk about that. So now the direction that we're going to have for this is going to be in the negative direction. There's a minus sign here. dB dt is a positive number. The area is a positive number. So the EMF overall is going to be in what we are going to call the negative direction. Now, how is the negative direction defined? If we take a standard coordinate system, a three-dimensional coordinate system, think back to your math classes, back when you were defining x, y, and z directions. If this is the x direction and this is the y direction, then z is coming out of the page. And that's what's called a right-handed coordinate system. And in all of these formulas that we use in physics, we assume a right-handed coordinate system, a standard mathematical description of x, y, and z. And that tells us that in a coordinate system like this is the direction of positive rotation. Remember from your math classes, positive angles are in this direction. Negative angles would be moving the other way. So this is what's considered to be the positive direction. So the EMF is in the negative direction. That's going to be back the other way. Okay, so there's an EMF that's being generated. Now what's interesting in these examples that we looked at in chapter 29 is that the EMF can be anywhere in the circuit. In fact, the EMF can be everywhere in the circuit, and that's what we've got in this situation. We have a very symmetric situation set up here. See how that loop has been placed symmetrically within this magnetic field region. And so what that tells us is that the EMF is not concentrated in just one region. There is an EMF in all regions throughout the entire circle. And that's happening due to an electric field. It's the force here being used to generate the EMF is not a magnetic force. We've looked at both examples in class. We've looked at examples in chapter 29 where it's a magnetic force that's pushing the charges and creating an EMF, or there's an electric field that pushes on the charges and generates the EMF. So in this case, in order to vary the magnetic field, we had to have charges that were accelerating. And those charges have also generated electric fields. So it's not the magnetic flux directly. It's not the magnetic flux that's pushing on the charges. It's the electric field that's being generated. And the electric field is being set up in circular loops, and it turns out that the wiring we have is placed within those circular loops, and that's why there's an EMF. So the key takeaway here is that the EMF is being generated by electric forces, electric fields, and that those are uniform throughout the circular loop that we have. So they want us to calculate how much current, and we can take the voltage, divide through by the resistance. It says 1.93 milliamps. Now, in part C, so this should be pretty straightforward. Now, in part C, it says, if I pick 2 points on the circuit, which would be at a higher electric potential. Now, this is a bit tricky because if I've got an electric field set up in circular loops here, right, and there's an electric field, you would think that's going to guide us in the direction of the EMF that's being generated. But remember, the EMF is being generated everywhere, so there's a combined effect all the way around this circular loop, but there's also resistance that's uniformly spread throughout. So what's happening is, we said that the overall resistance is 15 ohms, and assuming this is a uniform loop of wire, which I'm going to assume it is, so then that 15 ohms is uniformly distributed. And so it's kind of like having the EMF is uniformly distributed everywhere, the resistance is uniformly distributed everywhere. So it's kind of like, I got a little bit of a voltage boost, but I had a voltage drop. Voltage boost, but I had a voltage drop also. So everywhere along here, we keep having these voltage boosts, but we have a voltage drop at the same time. So the electric potential never varies. It doesn't increase, and it doesn't drop. And so the electric potential would actually be the same at all locations. If I put a voltmeter here and here, it would read 0. If I put a voltmeter here and here, it would read 0. Here and here, it reads 0. There's no voltage differences, because as soon as that EMF generates a little bit of a voltage boost, the resistance drops that, it uses that voltage up. All right. So if you could, so let's do a contrast here. Back when we were looking at batteries and resistors, the EMF was in the battery, the voltage drop was in the resistor. But here we've got the EMF is at all locations, it's spread out along the loop, and so is the resistance. And so we never acquire a net voltage anywhere. Questions on that, let me know. Let's move on and take a look at this third problem. So in this third example, we're moving on and taking a look at actually at an AC circuit. Now, one of the things that we've talked about in class is when you're given a, at this point in the course, when you're given a problem with a circuit, the first thing to check for is read the problem carefully and find out, do I have a DC power supply, which typically would be a battery? Do I have a DC power supply? Do I have an AC power supply, which it should tell you? Or do I have no power supply at all? So do I have a battery? Do I have an AC power supply? Or do I have no power supply at all? That's going to really determine how you solve the problem. Now, this is an AC power supply. And for AC, here's the circuit. Oh, I'm glad it's here. I was looking up and seeing, maybe I hadn't drawn one. So here's my AC power supply. Now, AC power supplies have two properties. They have voltage, which is usually given in RMS, and they also have a frequency to them. So our power supply, we are told, has a frequency of 60 hertz. Now, frequency in hertz is not standard units, so I've converted into radians. And what we have found is 60 hertz is a really common number that shows up in homework problems, and that's because that's what we run our electric power plants. The generators, the electric generators in power plants follow a standard of 60 hertz. If you pick up pretty much any electrical appliance, it's going to say this is designed to plug, anything that plugs into the wall outlet. Anything that plugs into an outlet is going to say it's designed for 60 hertz. And so in radians, that turns out to be 377 almost exactly. So that's pretty handy. Now it says that we have in this circuit, we've got not just the power supply, but we've got a capacitor, a resistor, and an inductor. We got all three, one of each. They're all in series, and that's a good thing because that's the only examples that we've actually looked at and have experience solving. And so I've got a series LRC circuit driven by an AC power supply. Lots of numbers to keep track of here. So we've got the frequency, we've got the resistance is given, the capacitance is given, and the inductance is given. Now, since this is an AC circuit, the capacitor and the inductor are going to have resistance-like properties. Now, we call it reactance, but as you know from class, this is measured in ohms. These are the reactances of the inductor and the reactance of the capacitor. We have formulas that we've derived for those, so plugging in the frequency allows us to determine what are the reactances of the capacitor and the inductor. Now, the first part of the problem, apparently, let's see if that's correct, says draw a phase diagram showing resistance, reactance, and impedance. So resistance, that's the resistor. Reactance, that's the resistance in the capacitor and the inductor. And the impedance is the combination of everything. Now, I can't just add the numbers together. It's more complicated than that. And that's because what we've shown is that the voltages across the resistor, inductor, and capacitor are out of phase with each other. But using these phase diagrams or impedance diagrams, this allows us to keep track of everything, taking the difference in phase into account. So what we do is in the horizontal direction, we draw a phasor representing the resistance in the resistor. In the vertical direction, we draw a phasor representing the resistance or the reactance due to the inductor. And then in the downwards direction, or in the negative y, the reactance for the capacitor. And that's 1965. It looks like the capacitor is going to kind of dominate here. Let's see what happens. So we got the reactances determined. What about the impedance? What about the combination of everything? Okay, so we drew the diagram. Now, I intentionally drew XC bigger. Did I get it right? I didn't really scale this the best. This is actually more than twice as large as the resistance. So XC, if I was more careful, could be much larger than R and much, much larger than XL. That's actually quite small. Now, what happens on the diagram is we first of all look at the vertical axis, and we take the difference between the resistive effects of the inductor and the capacitor. Now that's interesting, that because they're out of phase with each other in terms of their voltages, their reactances actually will cancel each other. And so what I can do is take the XL and subtract the XC. That's 1965 minus, or 279 minus 1965. In any case, these get squared. So for right now, that doesn't really concern me which way I'm taking the subtraction here. And then I square the resistance using Pythagorean's theorem, and I come up with an overall impedance, and that overall impedance works out to be 1710 ohms. Now, how did I get an overall impedance, a resistance, that is less than the reactance of the capacitor? Well, because it canceled with the inductor. These two numbers opposed each other, so I got some cancellation here. The overall impedance for the circuit is at 1710 ohms. All right, so that's the Z value, and so this is what the diagram looks like. What I've done is I've taken the difference between XC and XL, and I've identified it as being right here. So this is XL minus XC, and then I've come across here horizontally, and then I've dropped down the resistance. That's gonna, it's like vector addition. If you understand vector addition, or if you're able to do vector addition, you can do the impedance calculations that we have here. Okay, or the impedance diagram. What we can do now to calculate the net current is to take the voltage, divide through by the impedance, and that will give us the current. So for AC circuits, we have to take into account all sources of resistance. The resistors, the capacitors, the inductors, combine them all together. And so everybody is getting the same current because it's a one-loop circuit. That's only one loop. So whatever the current is here, that's the same as the current here, same as the current here and here. The current's the same everywhere. Now it's AC, so it's alternating, and if it's a standard AC outlet that we've attached it to, it's going to be a sine function. That is going to be varying as a sine function. Let's see. In part C, they want us to come up with values for the voltage across the resistor, voltage across the inductor. So what this would involve is, if we get out our voltmeters, if I put my voltmeter across the battery, what does it read? I don't know, because they never told us, right? They never told us the voltage. They ever told us the voltage in the battery? Yes, 120 volts. There it is, finally. I didn't get that written down. Oh, I got it written here. Okay, so if I put my voltmeter across the back, so it is a standard outlet. It's 120 volts, and it has a frequency of 60 hertz, which is 377 radians per second. We go out to all the hardware stores and all the appliances and cross out the 60 hertz and replace it with standard units of 377 radians per second. I'm sure everyone would appreciate that. Let's see, so that would read 120 volts AC. I've got to have my voltmeter set on AC. If I put my voltmeter across my capacitor, what's that going to read? Well, I can now come back for each of these devices, the capacitor, the inductor, the resistor, and I can take the R value or the XL or the XC, multiply it by IRMS, and I can calculate individual voltages. Now, the individual voltages are out of phase with each other. And so, again, just like we saw with resistances, I can't just add these all together and expect to get the total voltage across the entire circuit. Just in the same way that Z was less than XC, the total voltage, 120 volts, it's going to be less than the voltage across the capacitor. Some of the voltage across the capacitor is being canceled due to the presence of the voltage across the inductor. These are exactly out of phase with each other, a half cycle out of phase, and so those two voltages cancel out. Now you might also think, well, for the voltages to cancel out, do I need to have the capacitor and the inductor right next to each other? And we don't. The only requirement here is that they're both in series with each other, and so whatever voltage is here at some instant will cancel with some of the voltage that's here at that same instant. So at any given instant, we could add the voltages together throughout here to figure out the total voltage, but these are not instantaneous voltages. These are the RMS voltages. Those are the highest values of RMS voltage readings we would get if we were looking at the individual components. Questions? All right, let's move on and take a look at that last example. And then we have another set of problems to look at after that too. So here we go. Here is the last problem on this particular set of midterm examples. And what it says is that we have a microwave source. So here we're looking at fields that are propagating, electric and magnetic field propagation. And it says that we have a microwave source that is operating at 27 gigahertz. So this could be some kind of communication device, right? Now it says that it's actually, this device is producing pulses that last only 1 nanosecond. Wow. So it only turns on for a nanosecond and then it turns off. And it comes back on for a nanosecond and then it turns off. Now, the pulses that are being sent out are 24 centimeters. Now that's a diameter, so I got to remind myself the radius is going to be half of that. And it says that while this microwave source is turned on, the power during that time is 20 kilowatts. But then it goes off. What's the wavelength of these microwaves? What's the total energy of each pulse? What's the energy density? What are the electric and magnetic fields? So in class, we've derived formulas which I claim would help simplify all this. I hope they do. You're welcome to use the textbook's approach, or you can use kind of the unified approach that we introduced in class. Either way, but here is this beam. So here is this microwave signal going out. Now apparently it's circular because they gave us a diameter. And the diameter here is 24, so immediately I wrote that down as a radius, and then I converted to standard units. Now while it's turned on, it's operating at 20,000 joules per second. So those are the numbers that were given. Now for part A, they're just asking about wavelength. They gave me a frequency. And I know that for light, for electric and magnetic fields that are propagating, the speed of propagation is the speed of light. It's kind of the same thing here. And so we can write down that C and lambda and F are all related by that formula. So C equals lambda F is how those things are related. That allows me to write in the speed of propagation, the speed of light, and divide through by the frequency, which was 27 giga, is 10 to the 9th. And that says the wavelength for these microwave, for this microwave source is 1.11 centimeter. And that's, that's a pretty typical wavelength for something in the microwave part of the spectrum. So that seems fine. Now, the energy contained in each pulse, remember each pulse operates at 20,000 joules per second, but it's only on for a billionth of a second. So that's only 20 microjoules of energy in each pulse. So that's the energy contained. Now in part C, they start asking about, let me see if and we don't have to answer this in any particular order. So that's important too on exams, is if you get to part A and A isn't making sense, go on to part B and see if you can work from there. Maybe I can do B independently and then come back to A, because it will start to make more sense for me. Sometimes in part A I end up solving parts B and C, and so whatever order the answers come in, that's fine. You guys know that, right, from taking exams in this class and other classes. So let's do this. Let's see. Oh, the average energy density. So what we can do is we can take, what I did was I actually went back and solved for, or wrote down formulas for intensity in terms of energy density, so I can remind myself that the energy density can be calculated in terms of intensity divided by the speed of light, the speed of propagation. Now, the intensity is defined as power per area, and the area is pi r squared. So what I did was I calculated the intensity. Now that would be the power divided through by the area. Now this is a beam that's maintaining a diameter. So I can take that 20,000 watts, 20,000 joules per second, divide through by the area that it's concentrated in, and that says that we've got an intensity of 4.4, 10 to the 5 watts per square meter for this source. So that's 442,000 joules per second per square meter in this beam. That's how concentrated it is. And then the energy density can come from taking I over C. Now that turned out to be a small number, and we've talked about this too, I think, is that light propagating electric and magnetic fields can transfer an enormous amount of energy, but it transfers it so fast, we don't need a very large energy density in order to calculate quite a bit of energy. So the energy density here only worked out to be, if I take a cubic meter of space where this beam is passing through, I'm only getting a 1.5 millijoules of energy within a cubic meter of this. So it's not much, but it's traveling so fast that a lot of energy can be delivered. So it depends on energy density, which is not especially huge, but it also depends on how fast the propagation speed is, and that's a really, really, really large number. Okay, so we're transferring a lot of energy, 20,000 joules per second, with a relatively low energy density. Now in D, we're going after the fields here. So the energy density, we do bookkeeping with the way that we've defined electric and magnetic fields. So what it turns out is that the energy density, half of it's contained in the electric field, half of it's contained in the magnetic field. So we can write that down pretty quickly. Now the energy density of the electric field is 1 over 8 pi k times E squared. And so I can solve for the electric field using, and these are the formulas we introduced in chapter 31, which again is kind of a unified approach where we can do the electric and magnetic field with matching formulas. The electric field energy density looks like this. I have to remember the square root sign. This worked out to be 1.29 10 to the 4th newtons per coulomb. Now, this approach says that C times B is going to be the same thing as E. When we're looking at these fields that are propagating, it turns out that the propagation fields that we look at in chapter 31 are based on accelerating charges. They're not the fields that we've looked at in other chapters. It's a different sort of electric and magnetic field, specifically due to the accelerations of charges. And that's why we're finding that C, B, and E, well, in these conditions, they match. So I can write down the same number for each. Now, since they're asking about magnetic fields, I should also report that in Tesla. So by dividing through by a factor of C, I can get that number in Tesla. And that's what we've done here. So this is the magnetic field given in Tesla for this part of the problem. So we got the fields calculated. Now, let's see. The default understanding here would be, these would be the peak fields, huh? Because we didn't really do a, oh, I think we did. I think we did averaging. So as far as the power here would be an average power during the 1 nanosecond, and it said that. The average power is at 20,000 watts, and that means that these are RMS fields. That's an RMS electric field, that's an RMS magnetic field. Finally, in part E, A, B, C, D, E, if these microwaves strike an absorbing surface, how much force would they exert? Now, when we have an absorbing surface, the idea there is that the surface absorbs all of the momentum. So to calculate the force, what we're going to do is find out the rate at which momentum is being absorbed by that surface. Now, what we said here is that we're going to borrow a formula from special relativity, which we'll be learning here in just a couple weeks, is that momentum is equal to energy. For energy, I'm using U because E is already reserved for electric fields. So the big U here is energy divided by C. So for now, we're just going to say momentum is equal to U divided by C when we're dealing with light or photons or propagating electric and magnetic fields. And so that becomes the power divided by C, and that's not so much. It's 66.7 micronewtons. So when that pulse is hitting the surface during those brief nanosecond intervals, it's going to experience a force of 67 micronewtons for that time period. Okay. If it bounced off, if the light was reflecting off, perfectly reflecting, that would double the force, because not only would you absorb all the momentum, but the object would be pushed, the light, the electric and magnetic fields that are propagating away would get pushed back out. That would double the force. So reflecting surfaces are going to be twice as much. This was an absorbing surface. All right, that's a good set of topics that we've taken a look at. So let's stop there and take a break. We'll come back. We have one more of these practice sets of problems. So let's do that. I'm going to go ahead and take a break. If you guys have any questions, stop by.